Hello, I'm Maurice Dupre, and in this section we're going to discuss inverse trigonometric functions. Let's begin by looking at the inverse of the sine function, sine inverse of x. Here I have a picture of the graph of sine inverse of x. Y equals sine inverse x has its minimum at negative pi over 2 as a value, and its maximum value is plus pi over 2, and its domain is the range of x's from negative 1 to 1, the closed interval from negative 1 to 1. To see how this graph originates, notice that here I've drawn another picture with the diagonal line y equal x drawn as a dashed line, and to draw the inverse of a function you reflect in the diagonal line. If I draw the reflection of the blue curve in the diagonal, you'll notice what I get is a nice piece of the standard sine curve. In other words, if we allow this to continue on, you recognize what you see as a sine wave. And in order to invert the sine function, because the sine function itself is not one-to-one, what we do is restrict its domain so that it becomes one-to-one. Between negative pi over 2 and pi over 2 on the x-axis, notice that just this piece of the sine curve is one-to-one, and so reflecting that in the diagonal gives back the sine inverse curve. So there we have it, this nice sine wave going vertically. It's in effect a sine wave going along the vertical axis. Notice the sine inverse of 0 equals 0, and the tangent line has slope equal to 1 because the tangent to the sine curve has slope equal to 1 right here at the origin. And of course, if you reflect that line, it just becomes itself again. Now let's consider the tangent function and its inverse, the inverse tangent. Here I have the graph of y equals tan inverse of x. Notice that as we go out to positive infinity, tangent of x asymptotically becomes, tan inverse of x rather, asymptotically goes to the value pi over 2. It never reaches it, but asymptotically as x goes to infinity, it becomes pi over 2. That would be precisely the limit as x approaches infinity of tan inverse x is pi over 2. In the negative direction, it becomes negative pi over 2 at negative infinity. That is, the limit as x approaches negative infinity of tan inverse x is negative pi over 2. Notice here at the origin, the tangent line has slope 1 because the tangent itself at the origin had slope 1. If I draw the diagonal line, here I've done it on this picture, the diagonal line y equal x, the vertical lines x equal pi over 2 and negative pi over 2, then we know that the tangent function goes asymptotically off to infinity as x approaches pi over 2, and it's coming in here with a slope 1 at the origin, and then goes asymptotically down to negative infinity as x approaches negative pi over 2. And so consequently, we see the tan inverse picture as just the reflection of the tangent curve. Now let's look at the graph of the inverse secant of x. Here I have the picture of the graph of y equals secant inverse of x. Notice that the secant inverse of x is undefined for x between negative 1 and 1. In other words, the domain of secant inverse is all real numbers whose absolute value is greater than or equal to 1. So we should put this condition in there, absolute value of x greater than or equal to 1. Notice the value at plus 1 is 0, whereas the value at negative 1 is pi. To see how this originates, notice here I've put the diagonal line y equal x, and remember when we look at secant, the secant function, it itself is 1 over cosine, and we know cosine 0 equals 1, and we know cosine of pi over 2 and negative pi over 2 gives 0. So consequently, you have, in fact, these vertical asymptotes for the secant function, because cosine is going to 0 at negative pi over 2 and pi over 2. And so consequently, the secant function, remember, its graph comes up like this. And then over here where cosine's negative, it would be way down below the axis. And so if I reflect this piece of the secant function up to the diagonal line, it gives me this arm. If I reflect this one, it gives me the arm of the piece that's down here below the axis. In other words, in order to make the secant function 1-to-1, you see this is not a 1-to-1 curve. If I cover that up, this part is 1-to-1, and of course doing the same thing with the branch below the x-axis gives us a 1-to-1 function which we can then invert. And so keep this picture in mind for the secant inverse. So it's only defined for absolute value of x greater than or equal to 1. Notice as x goes to positive infinity, it approaches asymptotically the value pi over 2, and likewise as we go out to negative infinity, it asymptotically approaches the same value pi over 2. Now, as far as the inverse cofunctions are concerned, it's useful to keep in mind the inverse function cofunction identities. For instance, cosine inverse of x is pi over 2 minus the sine inverse of x. Cotangent inverse of x is pi over 2 minus tangent inverse of x. Cosecant inverse of x is pi over 2 minus secant inverse of x. To see where these identities come from, just remember that the basic trig identity is that the cotrig function of pi over 2 minus theta is equal to the trig function at theta. So for instance, if I have trig function of theta equals x, that says trig function inverse x equals theta. Well, look at this identity. Cotrig pi over 2 minus theta is then equal to x, and so consequently cotrig inverse x equals pi over 2 minus theta. But theta is the inverse trig function of x, so we get pi over 2 minus trig inverse of x. In other words, for any trigonometric function, cotrig inverse of x is pi over 2 minus trig inverse of x. That trig function could be any one of the 6 trig functions, actually. So what does that mean for the graphs? Notice when I see this equation, cosine inverse x equals pi over 2 minus sine inverse x, as far as the graph is concerned, all I have to do is take the sine inverse graph, negate it, and then shift it up by pi over 2. So here's the picture, cosine inverse of x. Notice what we've done is the sine inverse graph, remember, it's the one that comes down here, comes in like this. It's the S curve down there. So if I turn it upside down, that negates it, and then shift it up, I get the cosine inverse of x. So there we have the cosine inverse of x. Same thing happens for the cotangent inverse. If I look at the picture of the cotangent inverse, notice it's really the exact same geometric shape as the tangent inverse. It's just been flipped over this way and pushed up by pi over 2. So now instead of going asymptotically off to pi over 2 at plus infinity, it's going off to 0, and in the negative direction goes off to pi, and it crosses the vertical axis at pi over 2. Same thing with the cosecant inverse in comparison to the secant inverse. And so consequently we see again it's only defined for absolute x greater than or equal to 1. Taking the secant inverse and replacing it by negative secant inverse simply turns things upside down, and so it gets this shape and we shift it, and so consequently here is the graph of the cosecant inverse. Now let's look at the derivatives of the inverse trigonometric functions. First, let's look at the inverse sine function. d over dx of sine inverse x equals 1 divided by the square root of 1 minus x squared, and that's of course valid for x in absolute value only less than 1. Because you see, even if the absolute value of x were to equal 1, we'd have a 0 in the denominator, and of course x can't exceed 1 in absolute value because then you have a negative inside the square root. Now notice that the derivative of the sine inverse of x and the derivative of the cosine inverse of x have exactly the same formula with the exception of this negative sign that appears in the derivative of the cosine x. Remember, these inverse function cofunction identities, cosine inverse of x equals pi over 2 minus sine inverse of x. So if I differentiate both sides of this equation, the derivative of a constant is 0, and that tells me the derivative of cosine inverse of x will have to be the negative of the derivative of sine inverse x. Notice the same thing can be said about the cotangent inverse in comparison to the tangent inverse. The derivative of cotangent inverse will have to be simply the negative of the derivative of tangent inverse. The derivative of cosecant inverse will have to be the negative of the derivative of secant inverse. And so here, the derivative of tangent inverse x is simply 1 over 1 plus x squared. The derivative then of cotangent inverse x is negative 1 over 1 plus x squared. The derivative of secant inverse x, remember it's only defined for absolute value of x greater than 1. It's greater than or equal to 1 for the secant inverse, and so when we differentiate it, we get 1 over absolute x times the square root of x squared minus 1, and of course that won't even be defined at absolute value x equal 1, since that would put a 0 in the denominator. So what's happening here is, as the tangent line, as you examine the tangent line of secant inverse, when you get to either plus or minus 1, it's becoming vertical, so that the graph in effect has undefined derivative at x equal plus or minus 1. And again, the derivative of cosecant inverse x would be simply the negative of the derivative of secant inverse x. Again, only defined for absolute value of x greater than 1. So the sine inverse and the cosine inverse derivatives are defined for absolute value of x less than 1, and the secant inverse and cosecant inverse derivatives are defined for absolute value of x greater than 1. How about the tangent inverse and cotangent inverse? Well, notice any x can be put in for those expressions, and there's no problem because you square a number and you get something non-negative added to 1. You get a non-zero denominator. Let's begin by working a problem with limits involving inverse trig functions. So here we have the problem of computing the limit as x approaches 1 from the left of sine inverse x. Remember, the domain of sine inverse x is negative 1 less than or equal to x less than or equal to 1. And so if we're going to take the limit as x approaches 1, it's going to have to be the left-hand limit here. Well, when we look at the graph of sine inverse x, we can see very easily it's a nice continuous curve, and so it's continuous at the endpoints even. That is, the left-hand limit at 1 is the value of the function there, pi over 2. And so what we have here is that this is simply sine inverse of 1 equals pi over 2. Well, how about the derivative of this function sine inverse x? Can you remember what the formula is? Derivative of sine inverse x is simply 1 over the square root of 1 minus x squared. Let's look at an example where we compute a limit at infinity for an inverse trig function. Here I want to compute the limit as x approaches positive infinity of tangent inverse of x. Well, let's refer to the graph. Remember, tangent inverse of x goes asymptotically to pi over 2. And so the limit as x approaches positive infinity of tangent inverse of x is simply pi over 2. And so consequently, we have that easy answer. Remember, if you can't remember the tangent inverse, the graph of the tangent function being sine over cosine has these vertical asymptotes at odd multiples of pi over 2. And so the graph has these S-curves repeated over and over and over. And so we know that the tangent function as x approaches pi over 2 is going asymptotically to infinity. And so when you reflect this middle curve, you get the tangent inverse. And so that means that as x goes to infinity for the tangent inverse, you're going asymptotically to the value pi over 2. Let's calculate the derivative of a function which involves inverse trig functions. Here I want dy dt, where y is the sine inverse of the quantity square root of 2 times t. Well, remember, the derivative with respect to x of sine inverse of x is 1 over the square root of 1 minus x squared. So by the chain rule here, we're going to be differentiating y with respect to t. In effect, our x is square root of 2t. So the chain rule would tell us dy dt is equal to 1 over the square root of 1 minus, now we replace the x by the quantity square root of 2t, and then multiply by the derivative of what's inside. The derivative of square root of 2t is simply square root of 2. So notice square root of 2t quantity squared is simply 2t squared, and so we get as our final answer, with a little simplification, square root of 2 divided by the square root of 1 minus 2t squared. Of course, we can see right away that the domain of this is only going to be square root of 2t in absolute value less than or equal to 1, which means absolute value of t less than or equal to 1 over the square root of 2. Well, what about this problem? We want to compute dy ds, where y equals secant inverse of 2s plus 1. Remember, the derivative with respect to x of secant inverse x is equal to 1 over the absolute value of x multiplied by the square root of x squared minus 1. And remember, that's only valid for absolute x greater than 1. Since we have to have a non-zero number in the denominator here, and we also have to have inside the radical a positive number. Well, so in effect we have 2s plus 1 as x, and so to differentiate with respect to s, we use the chain rule again. So dy ds is the result of replacing x everywhere by 2s plus 1. So we have 1 over the absolute value of 2s plus 1 times the square root of the quantity 2s plus 1, all squared, minus 1, and then by the chain rule we have to multiply by the derivative of the expression 2s plus 1 with respect to s, and so that would be 2. We could clean this up a little bit. Dy ds is equal to 2 divided by the absolute value of 2s plus 1 times the square root of, well, when I square the 2s plus 1, I actually square that binomial, we will get 4s squared. The cross term will be a plus 4s, and then a plus 1 minus 1, they'll cancel, and that's all that will be left. Now we could take out the 4 as a common factor, and when it comes out of the radical, notice it becomes a 2, canceling that 2 in the numerator. So finally we could write this even more simply as simply 1 divided by absolute value of 2s plus 1 times the square root of s squared plus s. Well, let's work a differentiation problem involving an inverse trig function and an inverse of the exponential function, namely the natural logarithm function. So here I have y equals the natural log of tangent inverse of x. I want dy dx. Remember, the derivative of natural log of any u with respect to x is equal to du dx, all divided by u. And so consequently, dy dx is equal to the derivative of tan inverse x, all divided by tan inverse x. And of course, the derivative of tangent inverse x itself is 1 over 1 plus x squared. So we have the quantity 1 over 1 plus x squared in our numerator, and down in the denominator we simply have tangent inverse of x. And of course, 1 over something in the numerator divided by something else, we can in effect multiply these denominators together, and we simply get 1 divided by tan inverse x times the quantity 1 plus x squared, all down in the denominator. Well, let's remember that the trig functions involve ratios of sides to triangles, and so consequently taking inverse trig functions can be viewed as actual angles. Let's look at a problem where we can solve with geometry. Here's a picture which is indicating an informal proof of the fact that tangent inverse 1 plus tangent inverse 2 plus tangent inverse 3 is the number pi. That's a pretty strange looking equation. I certainly wouldn't have guessed it. And if you look at this picture, you might wonder who would have thought it up. But in any case, let's look and see what it says. If I look at this point right here in the center of this bottom 2-unit square, notice that this line from this corner up here all the way down is simply going diagonally through each of the little squares. And what we have here is a 180-degree angle. In other words, in radians, that is pi. So in radians, this angle plus this angle plus this angle is clearly pi. Now, what is the tangent of this angle? Opposite over adjacent. Well, both sides are the same length, so the tangent of this angle is 1, and so consequently the tan inverse of 1 is this angle. Of course, in that case, we see it's obviously pi over 4. So to begin with, tan inverse 1 is pi over 4, but that is, in a sense, kind of irrelevant here. We're not going to actually need the value of that angle. Now let's look at the next angle. Here, I have obviously a right triangle. Notice the short side has length 1 if I'm taking these small squares to have unit sides, and so I can think of the vertical side as having length 2. And so consequently, the tangent of this angle is 2 divided by 1, which is 2, or alternately, the tangent inverse of 2 is this angle. Now let's look at this triangle, the big one. The tangent of this angle is this side here divided by this shortest side of the big triangle. And notice this side and this length right here are the same. Here's the length repeated, here's the length repeated. In other words, this long side in this direction is 3 times this side. And so if this is a right angle, it looks like it is, it's close. If that is a right angle, then the tangent of this angle being 3 says that the tangent inverse of 3 is this remaining angle. And so consequently, tan inverse 1 is this angle, tan inverse 2 is this angle, tan inverse 3 is this angle, and so the sum of those being pi gives the equation. So in that sense, it's an informal proof. Now we can actually turn this into what in reality is a proof if we analyze it more closely. So let's look at the picture in more detail. Let's take the little squares to have unit sides. So the distance from A to B, we have to calculate that, and what's the distance from B to C? Notice whatever the distance from B to C is, the distance from A to B is 3 times as long. And in fact, the distance from B to C is square root 5. How do we see that? Well, the Pythagorean theorem tells us that the hypotenuse of this triangle has length equal to the square root of the sum of the squares of the sides. So we have 1 squared is 1 plus 2 squared is 4. So 1 and 4 is 5. This side, the hypotenuse of triangle CQB, is square root of 5. So we see the distance from B to C is exactly the square root of 5. Consequently, the distance from A to B is 3 times the square root of 5. What about the distance from A to C, what looks like to be the hypotenuse of a right triangle? Well, notice the diagonal of each one of these little unit squares is the square root of 2. And so as I go from A to C, I'm going through 1, 2, 3, 4, 5. And so the distance from A to C is 5 times the square root of 2. And so consequently, in order to prove that triangle ABC is a right triangle, all I have to do is show that the square of the distance from A to B plus the square of the distance from B to C adds up to the square of the distance from A to C. We've seen the definitions of the inverse trig functions. We've looked at their graphs. We've looked at their derivatives and worked some problems with derivatives involving inverse trig functions and their limits. Now that you've seen these problems work, you should try some on your own.